So random walks. This is a metaphor for really an astounding variety of different physical processes or physical things that go on in the world around us, restricted not just to physics, but these things show up in chemistry, biology, economics, all kinds of things where randomness and noise turn out to be important. So, the idea is something like, suppose I start standing at some position, and then every second I take a step, but I take a step in like a direction that I choose completely at random, right? This kind of noisy process, which, maybe this is what my trajectory looks like. This kind of noisy process, again, comes up in all kinds of different scenarios. And I want to think about this in contrast with a few other kind of like modes of moving around. So, one way that I could choose to move around would be to hold my velocity fixed, right? So if I hold my velocity fixed, we remember from the very beginning, or maybe chapter 2 of this class, that my position at the end of the day will just be whatever that constant velocity is times time, right? So if I, see how far I've gone in 1 second, and then I look after 10 seconds, I will have gone 10 times farther, right? Another mode of moving might be something like constant acceleration, right? Maybe, for instance, I'm holding a rock up in the air, and then I let go, and that rock starts moving with a constant acceleration, in this case, due to the attraction due to gravity, right? And, we saw, again, back in chapter 2, that if it starts at rest, and I define wherever it starts at to be like the origin, so I don't have to worry about its initial position, the equation here that we would use would be its position after some amount of time would be 1/2 times its acceleration, that constant acceleration times time squared, right? So if I look how far that rock falls in 1 second, and then I look, 4 seconds later, it will have traveled 16 times as far, right? 4 squared. Okay. Well, random walks are quite different. Random walks, this should be very different, right? It's not a constant acceleration, and it's not a constant velocity. The kind of metaphor here is something like, at every second, I'm changing the direction of my velocity or changing the direction of my accelerations, right? And so I wonder if I just pull up chat for a moment. Well, maybe I'll ask this question in just a second, actually. Okay, random walks. Where do I end up after a certain amount of time? How far away from where I started do I expect to end up? Okay, what's going on? What happens? Right, and there's some really kind of charming cartoons of this process. This one illustrating a random walk as if there was a rather tipsy person wandering aimlessly around a light post. There's also some things like here you see the DNA of an E. coli bacteria where the walls of the bacteria have been ruptured, and you see the DNA like spilling out from inside the cell. And if you look at the pattern of how that DNA has like unfolded itself, out here you see basically the DNA taking kind of one of these random walks around as it explores space. Really kind of beautiful, beautiful scenarios. I want to talk in this class about a very simplified version of these random walks that we can really understand pretty well. And so I'm going to call this the coin flip game, although it's really not going to be a very exciting game. The rules are pick a starting point. Pick a starting point, pick a number of times to flip a coin, So that's rule A, that's rule B. And then C is like step forward or backwards if coin is heads or tails, right? So I'm going to keep flipping one coin. I assume that's a fair coin, so it has a 50-50 chance of being heads or being tails. Being heads or being tails. And if it lands on heads, I'll take a step forward. If it lands on tails, I'll take a step backwards. This is kind of like a random walk, but only in one direction, right? So maybe I'll call like x, my position. So I start out at x equals 0, and then if I land on heads, I'll take a step 1 positive and tails 1 negative. Now in the chat, Sabrina has asked, if the directions are random, then surely we can't predict how far from our initial position we'll be. And actually, we'll see over the course of this lecture that because the directions are random, we don't have a very good way of predicting like what direction we'll end up being, but we can, in a statistical sense, predict on average how far away we'll end up. And we'll see that play out actually even in this simple coin flip game. And you will see the answer to this most recent question actually in just a moment. So what I want to do is kind of explicitly analyze this coin flip game for a few simple cases. So, case 1, let me say, is, 1 coin flip. Okay, so the outcome is either going to be heads or tails, which means my final position after I finish flipping this coin once will just be +1 or -1, right? With completely equal probabilities. Now, one of the things that I want us to notice here is that I'm equally likely to be positive or negative, and there's no way that I could have predicted whether my coin would land on heads or land on tails. So I'm equally likely to be in either direction. And that means my average final position is 0, right? And I'm getting that by saying 0 is equal to 1/2 times the chance that I am at 1 plus -1, right? Each of these two outcomes are equally likely. So the average, 50% of the time I'm at 1, 50% of the time I'm at -1. The average of those two things is 0. But my average distance is 1, right? And one way that I could kind of keep track of the fact that, being +1 or being -1 away from where I started has the same like magnitude is I could take the average of position squared, and this is equal to 1 here, right? So that's equal to 1. And here what I'm saying is I'm summing up with 50-50 probabilities. This is +1 squared plus -1 squared, and that's 1/2 times 2. Right? So again, what I'm doing here is to say I'm looking at the average distance, not between the 2 points where I could have ended up, but the average distance from where I started to where I ended up. Okay, so here's my number line. I started out here, and I ended up either here or here. And so the average of, in this case, say x squared, or the average kind of absolute value of the distance that I'm ending up, well, if I ended up here, the distance is 1. If I ended up here, the distance is 1. 1/2 times 1 plus 1 is 1. So there we go. So what we've seen is that even in this simplified version of a random walk, because my flips are random, my average position tends to be just wherever I started, but the average like distance away from where I started is not 0, right? Because on average, certainly in this one flip case, I'm never ending exactly where I started out. Okay. Let's see what happens when we look at 2 flips. 2 flips of a coin, right? So now the set of possibilities for flipping 2 coins is, heads, 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 tails, tails, heads, or tails, tails, right? And so what does this correspond to? Well, heads, heads means take 2 steps in this direction. So I might end up at 2. Heads, tails means take a step this way and then take a step that way. I would end up back where I started. Tails, heads, that's take a step to the left and then a step to the right. I end up back where I started. And tails, tails is take 2 steps to the left and I end up at -2. Okay. What I want us to notice yet again is that on average, I end up at 0, right? I'm equally likely to be at -2 and +2. Those kind of positives and negatives cancel out. There's also a chance that I actually end up back where I started. But so, if I look at my average final position, it tends to be where I started because I'm averaging positive and negative numbers equally together. Okay. Um, on so let me write that as average final position. And I'm going to use this notation where angled brackets mean take the average of whatever's inside, just so I don't have to keep writing average something, something, something. My average final position is still 0. I'm equally likely to go forwards as backwards. I have no way of predicting which is going to be which. And so my average position is exactly where I started. But my average squared position, which is a way of kind of helping me keep track of positive and negative numbers equally, well, I have an equal chance of doing any of these 4 options. So I'm going to take 1/4 times, well, I could have ended up in the tails position, and that would give me -2 squared. I could have ended up at 0 in 2 different ways, and I could have ended up at +2. Okay, and you can see that this is 1/4 times 4 plus 4, that's equal to 2. Once again, we see something with the same basic character as what we saw when we just flipped the coin once. My average position is exactly where I started because I'm equally likely to be either forwards or backwards. But that doesn't mean that my average distance away from where I started is also 0. Sometimes in this 2 flip case, I end up exactly where I started. And in other cases, I end up, 2 distance units away. Great, great. Before we kind of talk about the general case, let's just a little bit more briefly do the case of flipping a coin 3 times, right? And, it starts to get a little bit more tedious to enumerate all of these possibilities. Heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, 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 right? And if we say, okay, this is where I started, okay, 3 heads, that's like a chance of being at +3. Take a step to the right, to the right, to the left, to the right, to the right, to the left. That would bring me back at 1. So with this one, heads, tails, tails, that would put me at -1. Tails, heads, heads, that would put me at +1. Tails, heads, tails, that would put me at -1, -1. And then tails, tails, tails would put me at -3. Okay. So once again, we have a case where when I flip an odd number of coins, I never end up exactly where I started, but on average, I'm just as likely to go forwards as I am to go backwards. And so my average position at the end of the day is still 0. And again, it's just because I'm averaging positive and negative numbers together perfectly equally. On the other hand, it's not the case that I expect to not end up some distance away from where I started. All of my ending spots are different from where I started. They're +3, +1, -1, -3. And so we can quickly write this out. I wonder in the chat if everyone would go ahead and tell me what their guess for this answer is, or if you're able to quickly work out what, 1/8 times -3 squared plus 1, 2, 3, 4, 5, 6 times 1 squared plus +3 squared happens to be. An excuse for me to take a little bit of coffee. Sabrina, with the first guess of 3, is exactly correct. That's right. That is exactly right. And in fact, the general case here, yay, exactly, is that if you flip the coin n times, so n flips, your average final position is always 0, and your squared final position is n. Okay? And I want to contrast this with those other cases of motion. If you had, say, constant velocity, your average, say, position after some amount of time, like maybe we're imagining flipping a coin once per second or something, your average position will be, well, whatever your velocity is times time. And the square of your position, is going to be related to like time squared, right? Velocity times time squared, right? So a very different kind of way of moving, if you will. A very different way of moving. Now, in this general case where we have n flips, what we can do is look at like the probability of ending at some position versus final position, right? So for instance, if this is where I started, in the case of just flipping one coin, what I would draw here is like 50% of the time I end up one to the left, 50% of the time I end up one to the right. In the case of two coins, what I might draw is 50% of the time I end up where I started, heads, tails, or tails, heads. And then 25% of the time each, I end up two to the left or two to the right, right? And if I do this a very large number of times, what you end up with is a probability distribution that looks like something I can't draw, you know, this famous bell curve kind of pattern, right? Also known as a Gaussian distribution. Sometimes also called a normal distribution. A normal distribution. Okay. Something that I want to emphasize here is that this distribution of final positions comes from, if you like, adding up lots of results of a coin flip, lots of positive ones and negative ones that, you know, are happening randomly, and so the statement that, you know, in general, the average final position is still zero, you know, tells you that this distribution is kind of symmetric on both sides of zero. But the fact that, you know, the average of x squared, that's a statement that, you know, sometimes you end up, you know, various typical distances away. And it's kind of related to how wide this bell curve distribution looks. Okay, this coin flip game probably seems very much like a cartoon of, you know, the kind of process that I sketched over here. In the coin flip game, I'm only ever moving in one direction. And at every coin flip, I take a step of exactly the same size. Whereas you can imagine in a general case, at each moment, you choose a random direction, and maybe you move different amounts each time you take a step, for instance. But it turns out this kind of simplified one-dimensional coin flip game has all of the right features of these kind of simple random walk processes in general. And to give you a sense of the kind of interesting variety of cases that these things turn up, I want to have us do a little breakout room activity. So I'm going to post this link in the chat. Post that link in the chat. And here's the problem that I'm going to ask people to work on once we go into our breakout rooms. So suppose we have a small droplet of water. A small droplet of water. And I'll remind you that there are things like, you know, the density of water is like 977 kilograms per meter cubed, things like this. And it gets hit. It gets hit by an oxygen molecule. And I'm going to say this is a small droplet of water, like hanging in the air. So suspended in the air. It's at rest. For this problem, let's ignore gravity. So we have this like motionless sphere of water, and suddenly it gets hit by one of these oxygen molecules that's just whizzing around in the air around us. How big can this droplet be? How big can this droplet be if after the collision, it's moving with a velocity equal to its own radius per second. Okay, so just to kind of, again, state the question so that hopefully it's clear. And if you have any questions, please go ahead and ask. You have a little sphere of water hanging in the air, constantly being hit by the air molecules in the room around us. And I want to know if it starts at rest and then one O2 molecule bounces off of it, so that after the collision, this droplet of water is moving at a speed which is its size per second. How big was the droplet of water? The connection that I want to make here is that, if I have a little droplet of water and every time it gets bombarded by an oxygen molecule or a nitrogen molecule in the air or anything like that, if every time it starts picking up a velocity, which is like its own size per second, this droplet of water will basically move as if it's executing a random walk. Right? Now, we neglected gravity, and so this droplet of water will be constantly falling, but then getting collisions that sometimes kick it up a little bit, sometimes down, sometimes to the right, sometimes to the left, as molecules are hitting it randomly from all different directions. But if we get even a little bit smaller than this, these random collisions will be more than enough to kind of keep this droplet of water aloft and floating and executing this kind of random walk motion as it moves through the air, So this is one of the ways that like face masks work, right? I pulled up a data set that gave me typical sizes of different things, typical sizes of different types of things. So for instance, what I'm showing here is how big are things in microns, and 1 micron is 10 to the minus 6 meters. It's 1,000th of a millimeter. And you see various things, right? So like beach sand, that's hundreds or thousands or tens of thousands or hundreds of thousands of microns, right? So they range from millimeters, tens of millimeters, down to very small. Things like particles of smoke, that could be, tens of nanometers or 100 nanometers or something like that. Both atmospheric and household dust particles, are an enormous range of different particle sizes, as are things like viruses, bacteria, and importantly, the kind of water droplets that we exhale all the time or that we expel when we're coughing, right? And what I want you to notice is that the range of particle sizes involved in respiratory water droplets range from much smaller than the kind of estimate we just worked out, or the kind of estimate that I just worked out of hundreds of nanometers, to much bigger than that. So the first important thing to realize about face masks is that they need to stop an enormous range of different sizes of particles, right? And so the question is, how could a mask possibly do that? Masks need to stop an enormous variety of particle sizes. Ooh, and there's a question in the chat. An enormous variety of particle sizes. And how do they do that? An important thing is that a mask is not a sieve, right? So, so a sieve, like a kind of mesh strainer you might have in your kitchen, works by having holes that are a certain size. And everything that's smaller than a certain size, a sieve lets through. Everything that's bigger than a certain size, a sieve stops. And this principle could not possibly work for masks, because in order to make the holes small enough to catch, viruses or the smallest respiratory droplets, you would have to make a mask that would be impossible to breathe through, right? And so that's not a great solution, because it turns out breathing is important to us going about our daily lives. So a mask is not a sieve. It operates not according to this principle of just blocking big particles. It instead is kind of more like a spider web. The goal of a mask is to get, and this is like a zoomed in image of what an N95 mask actually looks like, a crisscrossing tangle of fibers with surprisingly big holes in some parts of the mask between all of those fibers, but many dense layers of these things. And here you can see for scale, some of these holes, 200 microns, are much bigger. 200 microns is like out here. That's much bigger than the size of the thing this mask is trying to stop. So a mask is not a sieve. It's more like stacked spider webs. Spider webs. So what a mask is trying to do is get particles to land, to touch one of the fibers that's composing it. And at the atomic scale, and at the molecular scale, and at the scale of these small particles that we're trying to stop, surprisingly, everything is sticky. And so if you can get particles to bump into one of these fibers, it'll stick there and it won't make its way into your mouth. So here's kind of the game. You have, here I'm looking at like a cross-sectional view of a mask. This is supposed to be a representation of this like crisscross tangle of fibers. And here is an enormous person's face. Great drawing. Great drawing. Strapped to an ear, I suppose. Should really take art lessons. So how does this work? Particles that are big-ish, big particles, basically move in straight lines. So if the particle size is much bigger than the thing we just estimated, every time an air molecule collides with that droplet, nothing happens. The inertia of a big droplet, something that's like tens of microns, is much too big to be affected by small collisions with the particles in the air itself. So these things basically move in straight lines. And that means that, eventually it'll hit one of these stacked layers of crisscrossing fibers. These masks are opaque because there's enough layers of them, even though there are big holes, that if you move in a straight line through it, you'll eventually hit one of the fibers. Small particles, like a little bit smaller than the things we just estimated, move in random walks. And so even if there's like a little breeze, the actual path that one of these particles will take is such that it really kind of explores the space, even as it's traveling through a mask. And it's basically guaranteed to hit one of the many fibers composing the mask, even though there are enormous holes in the mask on the scale of these particles. So because small particles take random walks, they get easily trapped. So it turns out, if you have not an N95 mask, but just any old piece of cloth, a few layers of shirt or something like that, that's enough to easily filter out both big particles and very small particles. It turns out, if I have particle size down here, and I have like mask efficiency on the x-axis, it turns out small particles and very big particles are both actually surprisingly easy to filter out of the air. And the challenge is kind of filtering out intermediate size particles. Those are the kind of particles that are small enough that they don't go in nice straight lines. They're big enough that they don't get lots of random little kicks from collisions with the air molecules. Medium-sized particles tend to kind of follow the streamlines of air and can be like deflected by your breathing around this whole tangled maze of fibers. And so just kind of pass through one of these masks and make it and potentially infect you, right? So it's these medium particles that are the most challenging. And by medium size, I kind of mean something very close to this threshold that we just calculated, where every collision is enough to almost move the particle into going at a speed equal to its own size per second. So something like, about 0.3 microns is kind of the hardest thing to filter out if you're a fiber-based mask. And so the rating system, like when you see an N95 mask, that means that mask is 95% efficient at filtering out this most challenging to filter particle size. Now, unfortunately, this most difficult to filter out particle size, 0.3 microns, you can see is right where both there are a lot of respiratory droplets and also kind of corresponds to the size of bacteria and virus that can fit inside of those respiratory droplets. So they're the hardest to filter out, and they're also some of the most important to filter out. So So manufacturers of high quality filters play lots of additional tricks to try to filter out these difficult things as much as possible. One common trick to do this is, for instance, electrically charged fibers are one really good solution. So if you make each of the fibers a positive electric charge, then things like virus DNA, which has a little negative charge to it, get attracted to the fibers, and that helps filter some of them out. Right? So, this 95 on an N95 mask means that the manufacturers have done something like this to make it very efficient, even at filtering out tough particles. It's automatically good at filtering out very small and very big particles. This N, by the way, stands for, is it resistant to oil droplets, which oil droplets can kind of remove some of these electrical charges, destroying the efficiency of a mask. And the N stands for, no, not oil resistant. You could also, in principle, find masks that are R95 or P95, standing for resistant to oil or oil proof and 95% efficient. You could also get things that are 99% efficient or almost 100% efficient. It's just a naming scheme. Just a naming scheme. Okay, but isn't that interesting? It's like the fact that there's this characteristic size where even colliding with a particle in the air, one of these tiny gas atoms or gas molecules, is enough to transition you, if you're a droplet of a small enough size, from being governed by inertia, moving in straight lines, to executing some of these random walks. And when you execute a random walk, you like explore more and more space. And in this case, you're like guaranteed to bump into a fiber. I want to close this class by saying the reason Fermi estimation works is that in its own way, Fermi estimation is also a type of random walk. At least it is once you kind of think about these Fermi problems in the right way, right? So what might that look like? Suppose I have a question. I have so many questions. Suppose I have a question. One of the first things that we think to do is come up with, well, what is our biggest underestimate and our biggest overestimate? We have like an underestimate and we have an overestimate for this problem. And that gives us a range inside which we think we might find the right answer, right? And so we come up with different schemes for guessing inside of this range. For instance, that geometric averaging technique where you take, the square root of the product of these two guesses. But you could come up with any number of other kind of sensible ways of guessing in between this range. And so maybe you come up with a guess that's like here. And maybe the true answer is over here. So true answer. And this is our guess. If you like, you can think of this as starting at the true answer and taking a step in some random direction with some random size inside of this interval that you think the correct answer starts at. Right? So it's almost like a random walk in, or at least a random step in how big an error are you going to make. What happens when we think about subproblems? Right? For subproblems, what we're doing is we say the true order of magnitude of the answer is, and let's just say it's something, 10 to the y. So y is like the order of magnitude of this problem, of this problem's answer. And we've figured out that one way we can better estimate y, rather than just guessing from the beginning, is to break the problem down into smaller subproblems, right? Each of those subproblems has its own order of magnitude. And I don't have a great notation for this, so I'm just going to call it, 10 to the x times 10 to the y, or 10 to the x1, 10 to the x2, 10 to the x3, so on and so forth. And so our guess for the order of magnitude is x1 plus x2 plus x3 plus however many of these subproblems we've broken it down into, right? That's how exponents add when you multiply these kind of numbers together, right? So we learned to break Fermi problems down into subproblems that we would then all multiply together to get our final answer. And for each of these subproblems, it's like we end up with another kind of underestimate and an overestimate. Somewhere in this under and overestimate range, we think is the true answer. And we make some guess for what we think the actual answer is. We make some guess. And typically, we've been doing this geometric mean technique. But again, you could come up with other things if you wanted. And so it's like each of these guesses is like taking a little random walk step away from the true answer towards our guess. And just like in the coin flip game, where we were adding up plus and minus ones to get to our final position, plus one every time we flipped a heads, minus one every time we flipped a tails. Here, we're adding together our guesses, and we can kind of think about how wrong we are by thinking about adding together the difference from our guess and the true answer in each of those intervals, if we knew it, right? And that's like saying we're taking a random walk in the error that we're making. So Fermi estimations are taking a random walk in the errors we make. Okay, now intuitively, I think it kind of makes sense what's going on. Like for each of these subproblems, we have, a range of underestimates and overestimates. And it's like sometimes we probably guess too high, sometimes we guess too low. And when we multiply things together, our overestimates and our underestimates kind of help compensate for each other. So intuitively, I think it makes a lot of sense that, when you break a problem down into a bunch of steps, and then you get each of those steps a little bit wrong, but, your mistakes kind of help cancel each other out. I think that makes some intuitive sense. The mathematics of taking random walks tells you actually how much this idea helps, right? So, the math of random walks tells you quantitatively why Fermi estimates tend to converge to the right answer. And if you like, to the right answer. And if you like, they also help you figure out, well, when should I stop breaking a problem down into smaller and smaller subproblems, right? As we saw with this coin flip game, it's like if you keep taking random steps of a certain size, so that's like if you keep breaking down a Fermi problem into subproblems that have the same kind of uncertainty in your range of estimates, then taking more and more steps eventually gives you bigger and bigger errors, right? So you don't want to take too many steps. You don't want to have too many subproblems because then you're just guessing too many times. But if at each step you can reduce your overall range of uncertainty, then this kind of mathematics of random walks tells you you should prefer to take more smaller steps than fewer big steps at random to get to the right answer.